now I'm going to introduce you to the squeeze theorem, and this here is a proper full version of the squeeze theorem here. But because we're only doing kindergarten maths, we're not going to be too bothered about this. We're going to use the kinder version of the squeeze theorem. Okay, so the kinder version of our squeeze theorem is given by this here. Now what it's saying is that suppose this is our function here. Suppose you know that our function is always greater or equal to this function and always less than or equal to this function here. So basically, if you look at this graph here, you know this is our function here, f of x. Now we know that our function is always trapped in between this function and this function. Always trapped, always less than or equal to always less than or equal to h of x and always greater or equal to g of x. Basically, this is our function, and we know it's always being trapped in between the two functions here. Now, suppose you know the limit of this function here as x approaches a. So a is here, okay, and it has a limit of capital L. So basically, if you look at this here, if we know that the limit of this function here as x approaches a, so as x approaches a, suppose we know at a the limit is capital L here, okay, so it's right here, capital L. And we also know that the limit of this one here, as it approaches a here, is always, well, it's approaching also capital L. So it's approaching the same limit. Now, if the limit of this is capital L and the limit of this here is also capital L, then we know that this function, the limit of our function, must go through here. It's being squeezed. It's being squeezed at this point here. Well, our function is always being trapped in between these two functions. Now, if the limit of these two functions is dead on capital L, then we know that our function must travel through this channel here, through this tunnel here. Well, it's being squeezed. So in short, if the limit of this function here is capital L and the limit of this function here is capital L, then at a our limit for our function is also capital L. That's what the squeeze theorem is saying. So as a quick example, let's look at this one here. What's the limit of this function here? So at the moment you've got this block multiplying with this block here. Now if you look at the graph of sine of 1 over x, well, sine of 1 over x it's always, well, the biggest value of this here is 1, and the lowest value is negative 1. So this is our graph of sine 1 over x. It always oscillates between positive 1, negative 1, positive 1, negative 1, positive. Well, this here is always trapped in between 1 and negative 1. Okay. Now, if you look at this here, we are trying to work out the limit of this here. At the moment, you've got this block multiplying with this block here. Now, looking at this here, if you look at this block here, the highest value that this could be is 1, and the lowest value that this could be is negative 1. So let's look at this collectively. Now, the highest value that this whole thing here could be, the highest value that this whole block here could be is x squared, because the highest value that this block could be is 1. So 1 times x squared is x squared. So the highest value that this whole thing here could be is x squared. Now, what's the lowest value that this thing could be? Well, the lowest value that this collectively, the lowest value of the whole thing is when this is negative 1. So negative 1 times x squared, it would be minus x squared. So what I'm trying to say is that looking at this here, we can actually say that the highest value that this thing here could be is x squared, because because this thing here is always being trapped in between. Well, the highest value that this block could be is positive 1. So when this is positive 1, then the highest value will be x squared. Now looking at this here, the lowest value that this whole thing could be is when this thing here is negative 1. Is when this whole thing here is negative 1. And if you get negative 1 times x squared, that will give you. My point is that our function, which is this one here, is always being trapped in between this and this. Okay, so if we know that the limit, if we know the limit of this here as x approaches 0 here is, well, the limit of this here as x approaches 0 would be 0. Okay, the limit will be 0. And looking at this here, the limit of this as x approaches 0 is also 0. So basically our function here is being squeezed or being trapped in between 0 and 0. Well, if it's in between 0 and 0, then the limit of this whole thing here must be 0. Okay, so if you look at the graph here, you can see this is our function. This is our function f of x here. The red line here is our function f of x. Well, it's being squeezed in here. My point is that we established that our function h of x as x approaches 0 is actually 0. And looking at g of x, well, g of x as x approaches 0 is also 0. So that means, well, it means that our function is always being trapped in between the two, then the limit must also be 0. Okay, but the important part is this bit here. Our function here, we know that it's always less than or equal to x squared, and we know that it must be greater or equal to minus x squared. And because, well, the reason we know that is because this always oscillates in between 1 and negative 1. So we know that this here is true. Now, if that's true, if the limit of this is 0 and the limit of this is 0, then this here is being forced, while the limit of this will also be 0. Okay?